going to start this lesson off in a bit of an unusual way, just by drawing an array of numbers here. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And I'm not copying these out of any book, not that you can, not that I couldn't be lying to you and pretending I'm not, but it's actually quite simple to see what the pattern is. Every row starts and ends with a 1. To get any number within the pattern, you just add the two numbers above it. So for example, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, 3 plus 3 is 6, etc. So if I were to write down this next row, I start it with a 1, I finish it with a 1. 1 plus 5 gives me 6, 5 plus 10 gives me 15, 10 plus 10 is 20, 10 plus 5 is 15, and 5 plus 1 is 6. And this thing can go on as long as you're willing to make it go on. You could make it 100 rows if you wanted to, but the numbers start to get really, really big. We call this thing Pascal's triangle. Not that apparently Pascal invented it, because it's been around for hundreds of years, in fact hundreds of years before him, but he gets some credit anyway, did lots of working with it. So you might wonder, what the heck does this have to do with anything? I want to tie it to a couple of things that we've done. So first of all, these numbers also do relate to combinations. Silly combinations like 0 choose 0 equals 1, 1 choose 0, 1 choose 1, all those equal 1. If I go to the next row, 2 choose 0, 2 choose 1, 2 choose 2, that's the third row of the Pascal triangle. 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. And if I keep on going, you'll start to get to the numbers that we have at the bottom of the triangle above. 4 choose 1, 4 choose 2, 4 choose 2, which equals 6, 4 choose 3, which equals 4, and 4 choose 4, which equals 1. Now you might still at this point be wondering, why in the world are we writing all this down? And what it ties to is actually expansions of binomial terms. So something like this. What is x plus y to the 0? Hopefully if you see something to the power of 0, you automatically say the answer is 1. Now if I say, what's x plus y to the 1? Even that, when you say, oh, that's just x plus y, I'm going to write it as 1x plus 1y. If I do x plus y squared, you might take a second, boil it out, and come up with 1x squared. You'd have 2xy, and you'd have 1y squared. And you may not have ever even gone this far to do x plus y to the 3, but what it turns out to be is 1x cubed, 3x squared y, 3xy squared, and then 1y cubed. No accident here, or no coincidence, that these coefficients in these expansions are 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. If you ever went so far as to multiply out x plus y to the 4th, in other words, x plus y times x plus y times x plus y times x plus y, and do all the work, crunch all the, FOIL everything out, expand it, combine all the like terms, what you would end up with is 1x to the 4th, you'd have 4x cubed y, you'd have 6x squared y squared, 4x y cubed, and then you'd have y to the 4. And the coefficients again would follow the 1, 4, 6, 4, 1 of Pascal's triangle. Another way to write that, which will make sense to you more in a second, is to say that's 4 choose 0, x to the 4 minus 0, y to the 0, plus 4 choose 1, x to the 4 minus 1, y to the 1, and then 4 choose 2, x to the 4 minus 2, y to the 2, 4 choose 3, x to the 4 minus 3, y to the 3, and finally, next row, 4 choose 4, x to the 4 minus 4, which is 0, and then y to the 4. That seems extra long, but what it actually allows us to do is to write down or come up with the binomial theorem, or the theorem for doing expansions of binomials, which is on your formula sheet, which I'll start with the next example.